In this video, I'm going to explain about magnetic flux density. We know that magnetic flux lines are used very commonly to represent the magnetic field. Let us recall some of the important points about magnetic flux. Magnetic flux is denoted by phi, the symbol phi. It's a scalar quantity. Number of magnetic flux lines represent the strength of the magnetic field. Represents the strength. The strength of the magnetic field. So these flux lines are very useful for representation of the strength of the magnetic field. At the same time, the direction of these lines, the direction of the flux lines is the direction of the field. Is in the direction of the field. That means the magnetic flux lines originate from North Pole if we consider a magnet, the dipole, the magnetic flux lines originate from North Pole and terminate at South Pole. But these flux lines further reach the North Pole inside the magnet. So that's why we say that magnetic flux lines are closed paths. Magnetic flux lines are closed paths. Closed paths. At the same time, if you recall the electric flux lines, they are not closed paths. The originated positive charge and terminated negative charge. If negative charge is not there, the electric flux from positive charge, they keep moving towards infinity. They do not form any closed paths. Whereas magnetic flux lines are always closed paths. Now, let us talk about the vector B, magnetic flux density, a very useful quantity to express magnetic field. Okay, as already indicated, it's a vector and it belongs to a family of flux density. Flux density vector fields. So magnetic flux density electric flux density, they all belong to the family of flux density vector fields. Magnetic flux density, as the name itself indicating, it's a density which can be defined as flux per unit area. It is the magnetic flux per unit area. So based on this definition, it has a unit of Webers per square meter. Webers per square meter. That means WB per meter square. Or it is also represented in terms of Teslas. Tesla. So more meaningful definition, more mathematical definition is given by B is equal to delta phi by delta S. Limit delta S tends to 0. So this makes the complete definition or mathematical interpretation of magnetic flux density. So here the delta S is an incremental surface area. An incremental surface area. Surface area. It's a small surface area. Let us say delta S. Delta phi is the amount of magnetic flux passing through this area. Amount of flux passing through this area. So magnetic flux density is the amount of magnetic flux passing through a given surface area as the area tends to 0. So the limiting case is to be considered while defining the structure B. So the flux density B is defined at a particular point rather than a complete surface area. So that means if you take a considerably large surface, then B may vary from point to point. The flux may not be uniformly distributed throughout the surface everywhere. So because of that one, it is advisable to define flux density at a particular point. So this is implemented using the limit delta S tends to 0. So when the surface has to be tend to 0, has to be shrinks to 0, then the surface should be taken as small as possible to define B. So small flux passing through a small area can give the definition as the ratio of flux by area. So that's why the magnetic flux is defined for a particular point. So we can say that magnetic flux density B at a point is defined as so let us make the definition from that equation. Is defined as the flux passing through a small surface as the surface area shrinks to 0. So this is a better definition for B. So according to this definition, so I can write B as, once again, the flux delta phi passing through small area delta S as the surface area shrinks to 0 or tends to 0. Next, this gives the magnitude of B, the flux density. What about the direction? If you look at the right side of this equation, there are two terms there. First one is the flux, which is scalar. Then the area, surface area, that can be the vector. Right. So every surface area can be a vector having its direction perpendicular to its own plane. So B is a vector, so its direction is given by the direction of the surface S. So therefore, the direction concept is explained here. The direction of B is normal to the surface, is always normal to the surface delta S. That means if you choose a surface of some area delta S, then the normal direction to the surface is also the direction of the B, flux density B on the surface. But all if you are representing the flux density on the surface, then direction of the surface itself is the direction of the flux density. So that means B can also be written as A cap n is equal to the limit delta S tends to 0 delta phi by delta S. Okay, so this B is a vector here. So that's why the dot product gives its magnitude. So in the definition, we have only shown the magnitude. We have only shown the magnitude. So the magnitude B dot AN. B dot AN always gives normal component of B. We can better understand it like this. If there is a surface, let us say some area delta S, the direction of the surface is perpendicular here. If the flux lines are passing through the surface at an angle of theta with respect to the normal, then the amount of flux passing through this area is given only by the normal component of the vector. What I mean is, if this is the vector B, let us say, then this vector can be split into two components. One is the component parallel to the surface, another one is component perpendicular to the surface. Okay, so this particular component is perpendicular to the surface, so we can call this one normal component, and this is tangential, which is parallel to the surface. This BT doesn't pass through the surface, whereas BN completely passes through the surface. So that's why the normal component of any vector is given by the dot product of the vector with unit vector normal to the surface B. So based on this, B dot A cap N represents normal component of vector B that passes through the surface. So the amount of flux passing through any surface is given by its normal component. So now, so B dot A n cap is equal to, after applying the limit, delta phi becomes d phi, delta s becomes ds. So differential condition, ds represents a point. So b dot a cap n is ds. Okay, so delta s is a small area. Delta s tends to 0 means the delta s completely shrinks to 1 point of smallest possible area, ds, differential area. So after applying the limit, delta s becomes ds. So correspondingly, delta phi also becomes d phi. So in the next step, b dot, I would like to combine ds with a cap n because a cap n is the direction of ds. So both put together, they become ds vector. So the dot product gives the amount of flux passing through smallest area, ds, differential area, ds. So now, if we consider quite larger area, then the amount of passing through that larger area is given by magnetic flux phi, integration of b dot ds. Integration indicates addition. So using the flux density B, we can find the amount of flux passing through every differential area and can be added. So this gives the total flux passing through. This is the total flux through the area S. The area S. That means if the magnetic flux lines are passing like this, then if you choose a smaller surface area, then the flux passing, this amount of flux passing through this area is given by phi. If you choose a closed surface, let us say, if you choose a closed surface like this, assume that this block represents the closed surface, then see the amount of flux passing now. The flux entering from this phase are leaving from another phase. Since these magnetic flux lines are closed path, the number of flux lines entering this volume enclosed by this closed surface definitely leave from one or other surfaces. So that's why the number of flux lines entering is equal to number of flux lines leaving the volume through this closed surface. So that's why when we consider the concept of closed surface integration of B, that always gives us 0. That always gives us 0. Right. So carefully understand the difference between these two integrals. This is open surface integral and this is closed surface integral. So total flux through a closed surface always equal to 0. So I can state this equation that the net flux crossing A closed surface is always equal to 0. Always equal to 0. So don't forget about the adjective. The net, it is the adjective's magnetic flux. This is applicable only for magnetic flux, not for the electric flux. The net magnetic flux crossing a closed surface is always equal to 0. This statement is very important because this equation, what shall I call this equation as? Say, number 1, this equation is also called as Maxwell's equation. This is also called as Maxwell's equation. This is very well known as Gauss law. It's known as Gauss law in magnetostatics. You can easily guess why this is called Gauss law. That's because a similar equation is available in electrostatics also. So in electrostatics, the closed surface integration of electric flux density D is given by Q. But in magnetostatics, the closed surface integration of B is equal to 0. So both are Gauss law. First one is belonging to electrostatics and the second one magnetostatics. And both of them are called Maxwell's equations. Maxwell's equations in integral form. In integral form. That means they are applicable to surfaces. Integral form. We can also represent this Gauss law in point form. How? So this equation, we shall apply divergence theorem. Divergence theorem. So divergence theorem is the relation between closed surface integration and volume integration. So the divergence theorem, which we already discussed, is closed surface integration of any vector is equal to volume integration of divergence of the same vector. So by using this one, I can change this equation to volume integration of divergence of vector V. On the right side, 0 is there, so any integration of 0 is also 0. So right side, there is 0. Left side, there are two terms, divergence of B and dV. This volume is not 0, cannot be 0 because it is volume integration enclosed by the surface. Surface is already defined, so it encloses some volume, so volume cannot be 0. Since dV cannot be 0, delta at B must be 0. Okay. So since volume cannot be 0, since volume cannot be 0, then I can declare that the divergence of B must be 0. That's why it is right side 0. So this equation, this one is called Gauss law in point form. Gauss law or Maxwell's, any one of them. Maxwell's equation, but in point form. Point. So we have the flux density vector having its divergence 0. Having its divergence 0. In electromagnetics, any very well explained vector will be having their divergence as well as curl. So both are available. So now we have divergence of vector B, which is 0. Then I have a question in mind. What is the curl of this magnetic flux density vector? It means what is del cross B is equal to 0. To answer this one, let us recall Ampere's law, which is given by closed loop integration of H is equal to total current enclosed. The same Ampere's law in point form is defined as curl H is equal to J, right? But B and mu are related to each other by this equation B equal to mu H. Mu is the permeability. Mu is the permeability of the medium. Permeability of the medium in which H and B are measured. Permeability of the medium. And that is completely defined as mu naught into mu r. Mu naught into mu r. So we know what mu naught is and what mu r is. Mu r is relative permeability, relative permeability. It has no unit or no dimension. So that's why no unit for this. Whereas mu naught is called absolute permeability. Absolute permeability. So absolute permeability, nothing but permeability of free space. Permeability of free space. Permeability of free space or air or vacuum, whatever it is. So absolute permeability. So its value is given by 4 pi 10 power minus 7 henries per meter. So absolute permeability has a dimension of henries per meter. So totally mu has a dimension of henries per meter. So this is a constant for uniform medium, isotropic uniform medium. So B and H are related to this one. Since B and H are related to this one, we can write the Ampere's law in terms of B. That means in place of H, we can write B by mu, that is equal to J. So taking mu to the right side, we get the curl of magnetic flux density, that is mu into J. So this is the curl, correct? And what is the divergence of B? That is 0. So for every vector of electromagnetics, it is very important to know the curl and divergence of them. So these two will help us to address the numerical problems on magnetic field, right? So that's about magnetic flux and magnetic flux density. Before we wind up, I'll introduce one more equation here. B is also used to define vector magnetic potential. Here A is the vector magnetic potential, which will be discussed most probably in the next video. Vector magnetic potential. So the definition of vector magnetic potential is given by this equation. B is equal to curl of A. That's about magnetic flux density. Thank you.